All right, let's do section 9.2, page 454, number 19, which reads, identify the indeterminate form and evaluate the limit using L'Hopital's rule. And for number 19, we have the limit as x goes to 0 from the positive direction of cosecant x minus cotangent x plus cosine x. Well, that's quite a mouthful there. And I think that it's important to write trig functions in terms of sines and cosines. At least that's what works for me. So let's start by rewriting this as the limit as x goes to 0 from the positive direction of, and what is cosecant x? Well, it's 1 over sine x. And cotangent x is going to be cosine x over sine x plus cosine x. Now, we've talked about a number of methods for evaluating limits, and one of the first things to do is to graph. Now, another nice thing about writing it this way is it's going to make it easier to input it into your calculator. So I'm going to draw a little sketch over here of what I got. And I got something that kind of looks like that, with a discontinuity over here at negative pi and a discontinuity over here at positive pi. But I really just care about what's going to happen here when my curve crosses the y-axis. And it seems to cross the y-axis at 1. So that's what I'm going to guess that the limit's going to be based on my graph, but I still need to solve it analytically. So after we've made a graph, then we substitute in. So I'm going to have the limit as x goes to 0 from the positive side of 1 over sine x minus cosine x over sine x plus cosine x. And this is going to give me 1 over the sine of 0 minus the cosine of 0 divided by the sine of 0 plus the cosine of 0. And that's going to be 1 over 0, because we all know that that's what the sine of 0 is, minus 1 over 0 plus 1. And that's basically going to give us infinity minus infinity plus 1. And that plus 1 isn't really going to matter. So what I've really got is infinity minus infinity. And that's my indeterminate form. That's a nonsense number. It doesn't have any meaning. It doesn't make any sense. And I can't stop there. It's not an acceptable answer. And we talked earlier that when we got the indeterminate form of infinity minus infinity, that we wanted to try to find a common denominator. So I'm working with the function 1 over sine x minus cosine x over sine x plus cosine x. And a natural common denominator here is going to be sine x. And most of my work is done because this is already over sine x, so that's going to be 1. This is already over sine x, so that's going to be minus cosine x. So basically, I just have to take my last cosine x and multiply it by sine x, and now I have everything over a common denominator. And you can see that what I've got is one function divided by another function. And hopefully, when I substitute in again, trying to evaluate my limit, I'm going to get 0 over 0 or infinity over infinity. So let's try to do this here. Now I'm going to take the limit as x goes to 0 from the positive side of 1 minus cosine x plus cosine x times sine x all over sine x. And if I substitute in, I'm going to get 1 minus, and what's the cosine of x? 1, plus the sine of x is going to turn that whole term to 0. And then I'm going to divide it by the sine of 0, which is 0. So I'm going to end up with 0 over 0. And that is an indeterminate form to which I can apply L'Hopital's rule. And remember, with L'Hopital's rule, I take the limit that I have, And I'm going to take the derivative of the numerator and put it back in the numerator. So of course, the derivative of 1 is going to be 0. The derivative of cosine is going to be negative sine. And then I'm going to have to apply the product rule here to take my derivative. So I'm going to take my first term, which is cosine x, times the derivative of the second, which is going to give me another cosine x. And then I'm going to take the second term, which is sine x, and multiply it by the derivative of the first term, which is going to give me negative sine x. And in the denominator, I'm going to take the derivative of the denominator and put it there. And the derivative of sine x is cosine x. And let's see what we've got going on here if we simplify things a little bit, or at least organize it. So I've still got my limit as x goes to 0 from the positive side, but I'm going to have sine x plus cosine squared x minus sine squared x all over cosine x. And again, I want to try substituting in because that's really the easiest thing to do here. So if I substitute in, I'm going to have the sine of 0 plus the cosine squared of 0 minus the sine squared of 0 all over the cosine of 0. So as we've said before, sine of 0 is 0, cosine of 0 is 1, another minus 0 there, all over 1, and I'm going to end up with a limit of 1, and that agrees with what we thought we saw with the graph.